So, first of all, thanks to the organizers for letting me present part of my current work, something that I has been doing as a PhD student at the University of Copenhagen, working under the ERC grant of Oliver Gressel, who is my PhD advisor. And today I'm gonna talk about a recent work that I has been doing in collaboration with Paulo Benitez Chambay and Martin Pesa. And the work is about a multi-fluid project that we have that Paulo was mentioning something yesterday during the numerical session, and I want to comment about this. And after, I will show some applications to protoplanetary disk that might be interesting. So the basic idea is to have a framework where we can solve the equations for multiple species, and we eventually can include the mass transfer between different species and the momentum transfer. So I keep this quite simple today, just including continuity and momentum equation. But it's something that you can basically extend if you want to do some non-ideal MHD, for example, problems adding the ions and the electrons. Or you can add as well the energy equation. But so far, we're going to only focus on these two equations. So basically, in the continuity equation, what we could have is a mass transfer between different species. And in the momentum equation, I want to keep your attention to the momentum, the transfer of momentum, basically, the momentum transfer between different species. So I'm going to talk about that. And what we are assuming now is that the drag force is given by this expression that depends on the velocity difference and has some collision rate, alpha, which in principle is a function of the density and the velocities of the different species. So the question is, how do we solve these equations to do some astrophysics, right? And how do we solve it numerically? So I'm only going to talk about how do we solve the momentum transfer. So this only contribution to the momentum equation. And I'm not showing here the pressure and the other terms in the momentum equation, and I will later explain why we are doing this. But it's related with the operator splitting technique that we are using in Fargo 3D. But nevertheless, you can think about that you have a problem where you want to solve this equation and focus on that point for the moment. So what we did was a very simple thing. Maybe the most simple thing you can do is an implicit numerical scheme. So this only has, so basically this is the equation that I was showing in the previous slide, but discretized in time. There's no any spatial derivative, there's no any spatial discretization. So when you discretize this in time, you have some, you have an n index that give you the time step where you're integrating basically the equation. And when you do it implicitly, that means that the update follow this kind of rule where the velocity in the time step that you want to solve it depends on itself on that time step. So you need to solve the system algebraically, and then you have to invert a matrix. So you have to move around stuff in order to solve it. But this is the generic expression. And we are assuming that the collision rate is given in the time step, in the previous time step, right? So if it does depend on the density of the velocity, you assume that you are not going to put an implicit coefficient here, basically. So this is very interesting because it has many interesting properties that are very important when you want to solve numerically. One of those properties is the stability. It is asymptotically stable. That means that the error is bound, the numerical error is bound, and furthermore, the error decreases to 0 as soon as you increase the size of the time step, or as soon as you iterate the time step. Basically, if you integrate it for a sufficiently large number of steps, the error will decrease, and then your solution will converge to the equilibrium solution of the problem. And this is something that you can prove basically by direct calculation if you have only 2 species. But as soon as you have a generic system with an arbitrary number of species, it becomes more complicated because you have a matrix of dimension n that you need to study and you to understand how it behaves. And we did that in the paper that we published this year, was part of the paper. Another thing we proved was the momentum conservation to machine precision. We want to study the momentum transfer between different species, so we would like to conserve momentum, right? So that's also very important. It's something that can be proved as well for an arbitrary number of species. That's what I say, basically. And we also did some tests, including nonlinear drag forces. Nonlinear means that, or linear means that this coefficient alpha that's not dependent on the velocity, basically, the collision rate. But you can include a collision rate that is velocity dependent, and we did some tests, and we recovered the solutions remarkably well. So we can use and we can study or using this scheme for nonlinear regimes. And it turns out that it's cheaper than an analytical method, and it has another advantage as well. I'm going to mention later on, but it is cheaper because if you want to solve this equation, you don't need to solve it numerically in principle, right? You can solve the eigenvalue problem because in principle, if it's linear, right, in a linear drag force regime, you can solve the eigenvalue problem. If it's non-linear, maybe you can linearize or do something else. But if you want to do that, you need to solve an eigenvalue problem, which is very expensive, and you could be conditioned, but it also you need to apply some transformations to make the system symmetric, which requires matrix operations. So that's also another additional computation time that you need to account for. So we are just solving this using an inversion algorithm, partial pivoting with Gauss-Jordan method, which turns out to or prove to be stable despite being partial pivoting. So so far I only talk about the implicit scheme, but we would like to do some astrophysics, so we implement this method in Fargo 3D. Fargo 3D works, as Paulo was mentioning yesterday, as an operator splitting or dimensionally splitted. The idea is that you can split the momentum or continuity equation between source terms and advection terms. And what we did was our multiple species, and each species has some experiment and some force, some Lorentz force or pressure gradient or gravitational gradient. And after the velocity and the densities are updated, actually the velocities because it's a momentum equation, you make the species interact each other in the collision step, and then you advect the solution in the transport step, where you solve the continuity equation there as well. And the important thing about this is the right fashion to do this, because when you organize the splitting in this way, you can prove by paper and pen that this returns the right equilibrium solution of the problem, the correct analytical equilibrium of the problem. And it is independent whether you use the collision, whether you solve the collision using an implicit scheme or using an analytical method. In the limit, you will get the same result, the same equilibrium solution, and that's something that you can prove. It's in somehow explaining in the paper, so that's very important because this satisfies a lot of important properties. Now you can be always sure that your problem will converge to the right equilibrium as a function of time. So in order to test our method, we were doing a test suite. It consists in something like 6 or 5 tests that are in the paper. I'm not going to explain all of them. I'm only going to focus on one of them that might be interesting for this meeting, which is the radial or the background equilibrium solutions for a protoplanetary disk when you consider some axisymmetric problem. And so far, I didn't talk about dust. This is the first time I will introduce dust, because what we can do with this method is to solve dust, treating dust as a pressure fluid. But I also mentioned that we can apply our framework to MHD or to other species if you want to mix gases or other kind of physics. That could be done in principle. But now let's talk about dust. So what we did was find the test suite consists in analytical or exact solutions for many different problems that are general for an arbitrary number of species. That was something new, and part of that is a new background solution for this. There are this famous solution from Nakagawa where you assume a Keplerian background and you expand your equation assuming that the dark force is perturbation, and you get you keep only the first order term in the velocities, and then you have some solutions but for two species. But what we did was assume that the background is for the gas is indeed sub-Keplerian equilibrium, not Keplerian equilibrium, and then we put an arbitrary number of species, and then after that we find the solutions which correspond to the solid black curve. On top of that, all the points correspond to the numerical solution, and different curves correspond to different sub-Keplerian backgrounds. Basically, what you can see, typically in the two fluid problems, you have that the gas is moving outward and the dust will move inward. But when you add more species, then the dust migration becomes non-trivial, and some species will follow the gas, some others will move inward. But if you change slightly the Stokes number of the mass, you can revert the migration of some of the species. So in a general problem, you still don't know where the dust is moving, where each species is moving. So you need to figure it out. But you can do it analytically because the solution is in the paper. So you can use that information, basically. So another applications to dust dynamics. Where yesterday we were talking a lot about the stream stability, today as well. So it seems that it's relevant topics in planet formation. So we learned a lot yesterday. So if we have an arbitrary number of species of multi-species stream instability, we learned that we have a challenge now in trying to understand the dynamics of what's going on, because apparently the growth rate might decrease with the number of species. But so the nonlinear evolution of the stream stability might become non-trivial. But that being said, we can still study the nonlinear evolution of the stream instability and compare our results with results obtained with particles, for example. So in that sense, we are doing an exercise trying to validate the approach of treating dust as a pressure fluid against treating dust with particles. So the stream instability provides us a very well-defined problem to do that comparison. So we did that, and we compared our results with previous one obtained by Bay and Stone in 2010, based on previous result by Sean Hansen and Judin from 2007. So we have two different cases here, only one dust species, and what we are showing is the density evolution of the dust. And it's developing this characteristic of filament structure in both cases. And here we have the result from the paper, and here are the result of Bain-Stone. And what you can see, qualitative, that they both agree, right? But of course, a qualitative comparison is not enough. You want to understand quantitatively what's going on. So what we did was try to reproduce these cumulative density distributions. But we are not counting particles, we are counting cells, because we are treating dust as a pressure fluid. And the idea is that you have to basically count the amount of cells that have a density above a given threshold, and in that way you construct your cumulative density distribution. So for one of the cases, the agreement is I would say excellent, it's remarkable. What we are doing with particles, you're doing with fluids, and this case is the larger Stokes number. The case with has a Stokes number equals 1, so it works pretty well in all the. So you don't only recover the maximum densities that you can get, so all the probability distribution is also even the shape is also recovered. But when in the other case, we have a different problem. So we have some degree of agreement up to 512 square cells, but as soon as we keep increasing the resolution, the density keeps growing. The density that you find in this filament keeps growing. So something is happening there. We still don't have an answer for that. I think it's quite an open question. It could be that the instability is telling us something that we yet do not understand in the nonlinear regime. It could be that we are reaching some limitation in the approximation that we are doing with the dust. So I think it would be very interesting to have a very well-defined problem where we can compare particles and dust with basically particles and pressure fluids to see what are the limitations of both approaches and where we can apply one and where we can apply another one. But I think we still don't understand this, and there's no final answer. And just to finish, I want to mention that since the multi-fluid Fargo 3D version came out like 1 year ago, officially public, I think 6 months ago, something like that, a handful of papers came out. So it turns out to be very useful, at least for studying different problems. There was a paper where we studied the self-organization of the Hall effect in protoplanetary disk. We were trying to understand whether the structures that are generated by the larger scale magnetic field flux concentrations eventually can trap the dust. So another project was the one that Pablo was mentioning during his talk, where we have the planetary migration affected by dust. There is some non-ideal MHD shock test with treating the ions and the electrons separately. And also some another work from Philip Bieber, who is a PhD student as well in Copenhagen, and he was studying how a planet like Jupiter or Saturn, after they carve a gap, they could filter the migration of the dust. They could filter how different sizes, how different dust sizes or grain sizes could move through the gap or not. And they were applying some of the results to understand some dichotomy that exists in the solar system in the concentration of calcium aluminum. And there was also a very recent paper. So it looks like it can be very useful. And so as a take-home message, I think we have a very robust and precise and probably perhaps one of the most efficient schemes to simulate multi-species system. And I will let this as I think as one of the open question of I think one of the things that we would like to have in the future, which is a framework, for example, where we could include pressure fluids and particles and try to understand the limitation of both approaches and when we can apply one regime, when we can apply the other one, depending on the physics. So the fact that we prove basically that the multi-fluid project works very well, it doesn't mean that it can be applied to any different problem, right? Every problem we have a different condition for that, and you need to understand very carefully if the pressure fluid approach could be used there or not. And another thing that could be interesting to see whether when you go to a regime where particles, the crossing orbit of the particles dominate the dynamics, where you can find an effect, when you can whether you can measure a velocity dispersion and try to find an effective pressure that you can use in the pressure fluid approximation to see if you can recover the dynamics of the particles there. So that's all. Thanks.
Okay, thanks a lot. We have time for just a couple of questions, Simeon.
Interesting. So I'm not quite clear on the operator split approach. So the collision operator, so that's implicit. If you take an enormously large time step, that will result in all the velocities of the species being the same, right? Because that's the only equilibrium solution. So how can you then, because that step doesn't know about all the sources, so how do you get the...
So that step, the way in which implemented, because it's affected by the source, when you do it, that step accounts for the acceleration, accounts for the new velocity that you are obtaining from the source step. So basically, you have a source step that will update the velocities, and then you have some accelerations, and you can think that some constant acceleration that you have now in the collisions, and then you can solve the system taking account for that. So I can show you that with how we do it with pen and paper, but the code is doing that. So the operator split is taking care of that. You are converging to an equilibrium, which is given by the implicit solver, but is affected by the acceleration of the source step. So when you do the calculation, you can prove that you are converging to the equilibrium of the problem, basically, not the equilibrium that give you only the implicit solver. And that is because the velocities will have some will be affected by the source step. So I didn't put the full equations with the full operator splitting technique there, but yeah, it can be done.
I'm afraid I just need one very quick question and very quick answer because we are running out of time.
Okay, this is a very quick question. On the one that didn't give the same as Bayern-Stone, what was the difference in parameters compared to the one that did?
So the Stokes number was smaller.
Oh, so that was small Stokes number.
Yeah, was 0.1.
And
it was a bit more massive.
Okay.
The epsilon was a bit larger.
Okay.
But the Stokes number was smaller, was 0.1.
Right.
So the one that agree has larger Stokes number.
Oh, with these 2 points, we don't really know yet what causes these differences or anything. Okay, thanks.
Thanks.
Okay, thanks again, Leonardo. We can move on